Yeah, once again, let us see the number 4. Number 4, we will be talking about ripple carry adder and look ahead carry adder. Previously, we have seen the half adder, full adder, and parallel adder. Parallel adder. Good. So now we have seen that in half adder, the half adder, it adds 1 bit. Half adder does not use a carry out. It's okay. It's CO, that is carry out. But the full adder can add 2 bits. It adds 2 bits and it uses the carry out. See? Now we have seen that if you have more than 2 bits, we can parallel adders. We can use the parallel adders. Good. So now, in this section, for the ripple adder, the ripple carry adder, let us start by the ripple carry adder first. The ripple carry adder is nothing but the parallel adders. Parallel adders, as you have seen here, this is the full adder. That's the first one. This is another adder. This is another adder. This is another full adder. So now, friends, with these 4 full adder, we can add 2 numbers, but each number having 4 bits. As you can see, 1, 2, 3, 4. 4 bits for A, B, 4. 4 bits. So we can add 2 numbers and each number having 4 bits. Now, as you can see, this ripple carry adder, the carry out, this is carry out of the first adder is the carry in. This is C in, this is the carry in, this is the carry in, this is the carry in of the next adder, as we have seen it in the parallel adders. Good. So now, the problem is, here it has one disadvantage, is that this sum here, or the output here, of the next carry out will be found after getting this sum, because it is from the sum we generate the carry out. An example, 101 plus 0011. For example, you see, 1 plus 1, it is equal to 0. It's okay? That is 0. But carry 1. You see? Now, you see that the carry is got from the summation. If you don't do the summation, you cannot get the carry. So, addition. 1 plus 1, that is 2. 2 plus 1, that is 3. Or 3 is equal to 1, carry out 1. So you see that after adding is there we have a carry out. So meaning that, let us finish, 1. So it means that to get the next carry out, to get this next carry out, we have first to do the summation. So that from the summation, we generate the carry out. From the summation, we generate the carry out. From the summation, we generate the carry out, and so on and so on. So meaning that the disadvantage is that the ripple carry has a delay. There is a delay. We will have a delay in addition, because this one will be what after generating the carry out, because this carry out will be used in addition. So that delay, that is the big disadvantage. So in electronics or in digital, we try to see how we can minimize the delays. Now, how can we minimize this delay? We minimize the delay by using look ahead carry adder. Coming back to our full adder truth table, I just show the output because we are interested in the carry out. How can we generate a carry out without delaying, without using the summation? So we will see. But as you have seen, come back to the truth table of the full adder. If you want, you can also draw the. You can do the sum. If you want, you can use the sum. But we are more interested in the carry out. We are more interested in the carry out now. Where is 1? Yeah, the carry out is 1. 1. Can you see there? 1. Good. See that? Now, considering this, and as you know, remember the carry out in the full adder, we have seen that the carry out is equal to A and B plus in the OR gate, or if you want, I can draw. Remember this, please. A, B, C, in. Good. Now we have seen that OR gate, and this is the summation, this is the carry out. So as you see, the carry out is equal to AB. This is A XOR B, exclusive OR B, C in. Good. So the carry out is A C in or CI. It's the same. C in, CI, same. It depends on the notation you have. So dear friends, as you can see here, when does C out is 1? Number 1, let us consider this case. You see, where A and B are 1s. When A and B are 1s, the C out is 1. Consider again this case, this one and this one. So this one and this one. What is that case? On this case, it involves C in. It involves C in. So it means on this case, the first case, A and B are 0. That is the case. A and B are 0. This is the case. Okay? And on this case, you see 0 is 1, A is 0, here B is 0, but, A is 0, B is 1. A is 1, B is 0. But A C in is also 1. So you see that to get 1 there, C in is involved. Okay? Now, for this case, A and B, we have 1 when A and B are 0. This is the carry, we call it carry generator. Carry generator. The carry generator, carry generator, because, why is it called carry generator? Because A and B, when all A and B are 1, they generate a carry. We don't need C in there. When A and B are 1s, we generate a carry. Now this one will be called carry propagator. This is the carry propagator. Why is it called a carry propagator? Because we have a carry. The carry 1 is there when C in involves inside. So when C in propagates a 1, we have a carry. So that's why we can say this is G and this is P. So this is P, propagator, and this is generator. Okay? Now, so we can summarize this saying C output is equal to generator, okay, the generator, C out is equal to generator plus or propagator C in. So this is the function now we have. So dear friends, we can also generalize the equation using the carry in and carry out. If you can see, if you generalize C out is equal to G plus propagator C. But which C? Now remember the first C out here, it uses which carry in, it uses the carry in. What is the carry for C out, from the first C out? If you call it C0 or C0, it will be the carry out, the carry in, that is the carry in, which is the carry out from another, and a previous carry, -1. It means carry out -1. So this is the generalized equation. If you want, we can say the C in is equal to C in for the second one. So we can say this is a C in, because to have a C in, it comes from the previous full adder. So a C in is equal to the generator which is the AND gate of the inputs, or the propagator. The propagator is the XOR, exclusive OR of, and C out -1. So it means C out -1 for the previous. So if you have this C to get the C in 3, what is that? C in 3, it means is equal to A and B. It's okay. What will be C in, it will be the C out minus 1. So it is C2 minus 1. So it will be, this will be minus 1. So it comes from there. Good. So dear friends, this is, try to understand. To get a C out, it depends on the summation and the C in of the previous adder. To get a C out here, it depends on the C in of the previous. To get a C out here, it depends on the C in of the previous. It's okay? Previous. Okay. So now, friends, this is how we can generalize the equation. C in here, C in is equal to the propagator, the AB, the generator, plus the propagator, and C out minus 1. C out minus 1 from this one, minus 1. So it is C0. C2 here, the C in will be minus 1, it will be C1. C3, it will be C2 minus 1. So this is how the generalized equation. Now, the problem is, how can we remove this delay? Because the C in is coming from the previous. C in coming from the previous, as you have seen on the report, carry adder. But now, how can we get the carry in of the next full adder without waiting for the summation to get the carry out? That is the question. So let me rubber this and see how we can get, nota bene, how can we get a C in? It's okay, because the C in here depends on the C out, and we get the C out here after adding. You see, to get a C out here, to get a C in, to get a C in here, to get this C in, it comes from C out 1, and this C out, to get it, we have first to get the summation. It's okay. The same thing, to get the C in here, the C in comes from C2, C out 2. And this C out 2, to get it, we must have first add these two, and then add the 2 with the C in, we get the carry out. So now the problem, I say, how can we find a solution? Because this will cause a delay. We have said delay. Delay is there. To have a C out, it will delay by adding. Now, how can we get C out without waiting for this addition to be done? Let me rubber this and I come. Yeah, good. So now, as I was saying, to generate a carry in, the carry in for the next full adder, it will depend on the C out of the first adder. To generate a carry in on the next adder, it will depend on the carry out of the previous adder, and so on. So this causes a delay. But with the look carry adder, or LCA, look ahead carry adder, LCA, the generalized equation could be C in is equal to the propagator, as the generator first, the generator or propagator, C I minus 1. As I said, it will depend on the C minus 1, the carry in of the previous full adder. So that's why, if we say on the first adder, I is equal to 0, If I is equal to 0, what will be C out? C out 0. C out 0. So don't confuse out and 0. Maybe to not confuse, let's write out. C out 0. C out 0. C out 0 will be equal to G1, G0, because I is equal to 0, plus P0, and carry in of the previous one, minus 1. So minus 1. Okay? So it means here, what we have, we have we have A, B, and the carry of the first. We have the carry. This is the three information we have. We have A and B, and the carry of the previous full adder. So now you see that if you want to generate now the second carry out, I is equal to 1. I is equal to 1. When I is equal to 1, what will happen now? We will have carry out 1. It's okay. Will be equal to G1 plus P1 and carry out of the previous. What is the previous? The previous this one. The previous this one. C out 0. You see? Because we have found the C out 0, which will be the input of the second one. Oh, sorry. This, sorry. I have well, if you want to, you can call it C in, C out, because no. Let us call it C in. Let us call it C in, not confused. C in 0. Let us call it C in 1. It's okay? Good. Now, there C into now. C into now. Wait a minute. C in 0. Good. Which is will depend on the C out. Now, friends, as you can see here, to get the input, the C input, it is the C out. It is the so sometimes the C out, C in are the same. Something are the same. Now, or if you want, you can name it C out, C in, because C out will be the C in of the second one. It is the same. Now, what will be now? Okay, good. As we have, let us call it, this is the first equation, this is the second equation. So let us replace C in the second equation. Will be equal to G1 plus P1. It's okay. C in out. C in 0 is equal to G0 plus P0. C in minus 1. So you see that if you have the value of C1, you will get directly G1 plus P1, G0, okay, plus P0, P1, if you can write this. Sorry, we have forgotten. Let us distribution, please. Okay, G0, let us start by 0. P1 plus P0, P1, C in minus 1. So you can see that you can get the carry out, the carry in of the second, the carry in of the second without having this carry out. Not needed. Because if you have the carry in of the previous one, the carry in of the previous one, you can get the second one. Now let us look at when I is equal to 3. When I is equal to 3, what happens? The carry in, we want this carry. We want to generate this carry. To generate this carry, normally, it should come to the carry out of the previous. Good. So, I3 is equal to G3. It's okay. No, G3. No, wait. We are jumping. Let us find the 2. Oh, no. This is 2. This is 3. Okay. When is equal to 2. It's okay. Now plus P2 C in minus 1. C in minus 1. So the previous one. So that is the C in 1. It's okay. Because it depends on the previous one. So now the previous one is C in. Now replacing C in the formula, we'll get what? G3, G2 plus P2. Replace the C1, CE1, G1 plus G0, P1 plus P0, P1 and C in minus 1. So G1, P2 plus G0 P1, P2 plus P0, P1, P2, C in minus 1. So, dear friends, as you can see, to get the carry in of the third full adder, normally we need the output of this one, of the carry out of the previous. To get this, we need the previous. But with this look at ahead carry adder, we don't need the previous the previous carry out. We don't need it because look at the formula. When you have the value only of the initial, when you have the value of the initial carry in, this carry in minus 1, that's all. You can get the carry out. You can get this carry out. You can get this carry in, which is equal to the carry out. You can get this carry in directly. See? If I is 3, so if I is 3, it will be the same. If I is 3, I is equal to 3. So we will have C in 3 equal to G3 plus P3 C in, so the previous one minus 1. So it was 2, so minus 1, it will be minus 2. It's okay. So the previous one, it is C of 2. Okay. Now, taking the same equation, replacing inside, what will we have? We will have G3 plus P3 G2 plus G1 P2 plus G0 P1 P2 plus P0 P1 P2 C in minus 1. C in minus 1. So by distributing, you will have what? G3 plus G2 P3 plus G1 P2 P3 plus G0 P1 P2 P3 plus P0 P1 P2 P3 Ci minus 1. So dear friends, this is C in 3. So you can see that to have the input of the next full adder, you don't need to have, if you have more parallel adders, if it is 4 or 5 adders, to find the input, to find this, because it will depend on the C. As you can see, C out of the other one, C in of the second one. To get this one, it will be simple. It's just to have the first carry input 1 minus 1. If you have the carry in of the first adder, that's all. You can generate the last one. You can generate the last one without waiting for getting the summation. So this is how the carry look ahead carry adder works. So now remember again, we have seen the half adder, full adder, ripple carry adder, The ripple carry adder is the parallel adder. It's okay, parallel adder, and we have seen now the look ahead carry adder, which is very commonly used, so that it cancels the delay in this ripple carry adder, where the second input will be got, the second carry out will be found after the summation of the first previous full adder. So brief, these are the 4 adders where they are commonly used in different digital systems, computers, calculators, and in different areas. So the next function for the combinational logic is the comparator, decoder, encoders, which will come for the next session. Thank you.